Look closely at a large-scale chemical refinery at night. The high-pressure vessels, the miles of interlocked piping, the continuous venting of steam. When a facility like this breaches its containment, the result is rarely a standard industrial fire. It becomes a localized, weaponized atmospheric event. Mass casualty incidents of this scale do not happen because a single valve fractures or a single operator makes a mistake. They occur when every independent layer of defense, the mechanical integrity, the administrative protocols, and the human response, fails at the exact same moment. Using data from the U.S. Chemical Safety Board, we are going to reconstruct the anatomy of a catastrophic release, minute by minute. By tracing the forensic timeline of these major disasters, we can extract the strict engineering and safety protocols required to stop them. Preventing a mass casualty event requires a shift in perspective. A refinery must be viewed as a highly fragile architecture of interconnected safety systems, operating constantly to hold back immense physical energy. This photograph documents the aftermath of the Flixborough chemical plant on June 1, 1974. A temporary bypass pipe ruptured, releasing 400 tons of superheated cyclohexane. The resulting fuel-air explosion yielded the kinetic force of 15 tons of TNT, instantly killing 28 people and damaging 1,800 nearby buildings. This diagram illustrates the physical thermodynamics behind that destruction. When a highly pressurized liquid chemical breaches containment and meets atmospheric pressure, it rapidly expands into a massive vapor cloud. A few cubic meters of superheated liquid can exponentially multiply to blanket an entire industrial site in seconds. The precise chemical agent dictates the type of hazard, but the mechanical requirement for absolute integrity remains identical. While cyclohexane creates a massive thermal detonation, a chemical like liquid nitrogen creates a dense, oxygen-displacing fog. In 2021, a bent tube in a Georgia poultry plant released a cloud of liquid nitrogen that asphyxiated 6 workers. Whether the chemical is highly flammable, highly toxic, or cryogenic is secondary. The true danger is the massive reserve of physical energy waiting to exploit the very first structural weakness it finds. The forensic timeline of a disaster does not begin at the moment of rupture. At T-120 minutes, the foundation for catastrophe is already set. These events are seeded months or even years prior by deferred maintenance and an operating culture of normalized deviation. At Flixborough, engineers discovered a large vertical crack in reactor number 5. At the Foundation Food Group facility in Georgia, a liquid nitrogen bubbler tube was bent during routine maintenance. In both cases, standard mechanical integrity checks failed to mandate a permanent engineered repair. Instead of pausing production, management often improvises. At Flixborough, operators removed the cracked reactor and installed a temporary 20-inch dogleg bypass pipe supported by scaffolding. They entirely bypassed the management of change, or MOC, process. No qualified mechanical engineer analyzed the high-pressure stress loads on the temporary setup, and no pressure tests were conducted. A ruptured pipe or a bent tube is merely a physical symptom. The underlying disease is an organizational culture that accepts temporary workarounds as permanent operating solutions. At T-60 minutes, the physical anomalies are locked in, and the administrative safety barriers begin to fail. Process hazard analysis is designed to foresee abnormal conditions. Yet facilities repeatedly fail to anticipate pressure surges within temporary piping or neglect to install basic atmospheric monitors in hazardous zones like nitrogen freezers. Flawed operating procedures compound the latent mechanical issues. During the 2005 BP Texas City disaster, the procedures for restarting the isomerization unit did not match the actual physical process conditions. Operators were using obsolete manuals and lacked the specific training necessary to manage the highly volatile startup phase. This diagram illustrates the Swiss cheese model of accident causation. Process safety management relies on 14 distinct elements acting as defensive layers. But when hazard analyses are incomplete, procedures are outdated, and mechanical integrity is compromised, the holes in these defenses perfectly align, allowing the hazard vector to pass straight through. These administrative blind spots guarantee that when the compromised equipment eventually fractures under pressure, the human operators on the floor will have no warning and no protocol to stop the cascading failure. At T-15 minutes, the crisis crosses the threshold of survivability. Facility layout choices directly dictate the casualty count. At BP Texas City, management placed occupied, unreinforced contractor trailers directly next to a highly hazardous atmospheric vent stack, positioning dozens of workers squarely inside the blast zone. Here we see the mechanical layout of the Union Carbide plant in Bhopal, India, the site of the worst industrial chemical disaster in history. To mitigate a methyl isocyanate leak, the system relied on a vent gas scrubber designed to neutralize the chemical. However, to save on operating costs, the scrubber was completely deactivated. The redundancies were equally compromised. The connecting pipe to the flare tower, which could have safely burned off the excess gas, had been removed for maintenance. Furthermore, the massive Freon refrigeration system required to keep the chemical at a stable temperature was shut down entirely. The toxic release was mathematically guaranteed. When the release finally triggers, emergency response protocols disintegrate. Without strict HAZWOPER training or clear hazard communication, workers frequently lack the required personal protective equipment. As seen in the Georgia nitrogen leak, unequipped personnel will instinctively walk directly into an oxygen-deficient hazard zone to attempt a rescue, fatally succumbing to the invisible vapor. When alarms are deliberately silenced, critical scrubbers are taken offline, and responders lack protective gear, the facility exhausts its final margins of safety. It crosses the point of no return. At T0, the stored energy finally overcomes the tensile strength of the compromised metal. The lateral forces on a temporary joint or the internal pressure of a runaway reaction peak, and the seam fails. The high-pressure liquid instantly depressurizes, blasting into the atmosphere as a violent spray. This plume model charts the immediate aftermath. The chemical violently boils off into a heavy vapor cloud. Guided by local wind vectors and physical barriers, the lethal concentration gradient rapidly expands across the facility footprint, engulfing the processing units, the maintenance yards, and the adjacent administrative zones. The workers caught in the plume's path have seconds to react. Control rooms that lack blast-resistant hardening collapse instantly under the massive overpressure of a thermal detonation. First responders, arriving to what they believe is a routine structural emergency, are suddenly caught inside an expanding explosive or highly toxic perimeter. The final explosive yield, or the toxic footprint of the disaster, is not an act of chance. It is precisely proportional to the depth of the organizational negligence that allowed the physical hazard to escape. After these events, the Chemical Safety Board repeatedly draws the exact same forensic conclusion. The root causes of the 26 deaths at Flixborough or the 15 deaths at Texas City were not localized operator errors. They were deep organizational deficiencies executed at the highest levels of corporate management. The first step in the prevention playbook is stopping the release before it starts. This requires absolute adherence to OSHA's Process Safety Management Standard. Management of change protocols must be rigorously enforced for any mechanical alteration, any shift in operating parameters, and any reduction in safety personnel. This diagram illustrates the second step, surviving a release. Under OSHA's HAZWOPER standard, facilities must establish rigid emergency parameters. That means predefining hot, warm, and cold zones and mandating that no personnel enter the hazard perimeter without a strict decontamination corridor and appropriate protective equipment. Regulatory compliance serves as the only legally mandated engineered defense designed to counteract catastrophic physics. The hundreds of pages generated in a CSB incident report serve a singular purpose: to break the cycle of normalized deviation. By dissecting the systemic failures of the past, the industry can ensure that identical casualties are not repeated in the future. When corporate leadership sacrifices mechanical integrity and analytical rigor to accelerate production or hit budget targets, they leave behind a permanent, tragic legacy. Process safety professionals must aggressively audit their own facilities against these historical failures. Challenge your temporary bypasses, interrogate your hazard analyses, and verify your emergency isolation systems. To continue analyzing the exact regulatory and engineering standards that keep sites safe, subscribe to HSE Study. Chemical processing systems offer zero margin for error. In the presence of superheated liquids and toxic compounds, A rigorously enforced safety architecture is the only thing standing between routine operation and total catastrophe.